Okay, welcome to Lecture 2. Theories of Deep Learning actually should be question mark, as you see on our poster. And so I'll just remind you that we have a parallel course on Mondays, same time but in a different location, which is complementary because it should help you do the massive computational experiments that would be required to get into this subject. I'll just remind you of some course information, some of which you must know because you're here. We're Wednesdays 3 to 4:20. We're going to try to be, 50 minutes or so and then have discussion. We'd really encourage a lot of interaction here because the point of all of this ultimately is we're going to have guest lectures every week, and it's better if you're interacting with these people who come a long way to tell you about their work. Not much point of you not interacting. I'll remind you, which some people don't seem to have known, that we have a GitHub website, and so you go off the Stanford domain to access some of the information about the course, including the weekly reviews of what the different lectures are about and the recommended readings. I have office hours Mondays and Wednesdays at 1 p.m. in Sequoia 128. That's the home of the statistics department. And the co-instructors on this, postdocs, are Hatef Monajemi, who's right here, and Vardhan Papayan, who should be here somewhere, but may not have found the place. Okay, he just flew in from Europe, and so he's excused for not knowing his way around the Stanford campus. It's like his first day at Stanford. So as I said, we have weekly guest lectures, and there are associated abstracts describing the contents of the lecture. There are associated readings. We are going to have light projects. This is a one-unit course. So how much work can we actually ask, right? So Hatef has some observations about what will be required as work for the course.
So yeah, I just wanted to point out quickly that this course is a lot about discussion. So we want people to have discussions. So before any guest lecture that we're going to have, we'll ask students to read the assigned materials, and then you will post your questions on Canvas discussion forum because it's a pretty big class, and then either me or Professor Donoho or Vardhan will facilitate, and the last 20 minutes of each session that we have, you're going to have discussions about the questions that you might have. And during the class, if you have any question, you can still post on the Canvas forum that we have. And also, a lot of students contacted me about how they're going to be graded in this course. So the way we decided is that your course, basically the passing grade that you're going to get is determined by the contribution that you will have to these discussions. At the same time, you're required, each one of you, to write a review of one of the theoretical papers in deep learning. Could be the papers that we discuss in this course, or could be a paper that you've seen somewhere else and it's interesting to you. At minimum 2-page requirement for a review paper, and that's going to be the course grading policy. Is there any other question that you may have about the course policies? Yeah, please.
Just to be clear, what you just said is the project, is that project, right?
The 2-page review.
2-page review of a theoretical paper in deep learning. Yeah.
So as we've said, the course website has a set of information that overlaps with the Canvas site, but they're not the same. Main thing is the Canvas site has a chat or discussion section where you can post queries and we can curate them and extract to ask each week's lecturer. In addition, at the Stanford Canvas site, I took the liberty of posting some articles which are available to us on the Stanford network because our library privileges give them to us. So there's some copyrighted things, you know, papers from Nature or whatever that might not be out there except on the dark web or somewhere. On the other hand, the course website out on GitHub has more detailed information, and the reason we did it that way is it allows the speakers who are coming to place whatever they want out there. The speakers who are coming would not be able to get inside the Stanford domain to change things on the Canvas site, so we're giving them more of a chance to be involved. We're posting in both places lecture slides, so you can see slides of the last lecture slightly amended. I'll just say this is not a course about the basics of deep learning. There are many resources that are out there that you can consult. We mention a few of them here, and I think these are hyperlinked so that when you get the slides you would be able to just click through. But for example, for natural language processing, Chris Manning has a class that goes in detail over the use of deep learning in natural language processing. And there are courses by Andrew Ng, including at Coursera. There's also CS231N website, likewise at GitHub. And then there's a great set of tutorials at PyTorch, which span a lot of interesting examples. Finally, there are books, the most well-known of which is Goodfellow et al. But there's an online book, and there's many O'Reilly books. The O'Reilly books are kind of like, let's take this package that's available in Python or what have you, and let's do a few examples. There's a reading list here which has lots and lots of pointers to papers, including many NIPS papers. So there are a lot of resources out there. We're not going to go in detail over these. We're focusing on some very specific aspects raised by this whole movement, rather than trying to inculcate all the latest and greatest of the movement. We're trying to just highlight some questions that the movement has created and ask if theory can shed some light on them. So as you know from our course website, we have a sequence of lecturers. The next lecturer is Helmut Bolske from ETH Zurich, who's got a series of co-authored papers on the interrelationship between roughly modern computational harmonic analysis, including wavelets and similar ideas, and deep learning. Our last lecture will be by a co-author of Stéphane Mallat, who has also written a lot on the same topic. Because of the travel schedules of the different speakers, we can't necessarily get them to speak in the order which would be the most natural for comprehension here as a unified subject, but we can only do what we can do. For next week's lecture, Helmut Bolske has suggested out on our website a series of papers with very impressive looking titles about mathematical theories of deep convolutional neural nets. You may also find the more poetic style of Stéphane Mallat interesting. And many people have told me they get a lot out of his presentations. We have a partnership with the Alan Turing Data Science Institute in London. And so, for example, this morning, London time, they watched last week's lecture, which you were here for. No, we didn't send it by carrier pigeon, but it just took time to get all the editing done. In any event, they have a nice lecture by Stéphane Mallat, and we will embed the link in this particular PDF when it's posted, and you can go see his lecture. It's got lots of, as I said, inspiring way of thinking about things. Now, just to review, last week we went over a certain viewpoint of what this is and why it's happening, and essentially the point that we were making is that the global access to smartphones, which is penetrating everywhere on Earth, has led to a massive investment on the part of all the world's major economic forces to create a gigantic computational infrastructure to service those smartphones, and as a result, just a tiny, tiny sliver of everything that's out there in terms of computational power is enough to solve problems by brute force. So you don't need theory in that sense to make progress on certain kinds of problems. And by using that brute force, you can see that there's been tremendous progress, for example, in the ImageNet challenge recently. So it's not necessary to imagine that there were brilliant theoretical ideas. It's not necessary to imagine that any of the foundations of this are in any way deep or theoretical, despite the use of the word deep in there and despite the use of mathematical terminology. It's just simply an era where brute force has suddenly exploded in potential. Okay, so for this lecture, I just wanted to focus a little more on something that I brought in last time. And so we need an emblem for this lecture. So I'm proposing, here's our emblem, that we have pixel features that somehow then feed into edge features, that feed into object parts, that feed into object models. And then if you had different data, such as in one case a database only of faces, or in another case a database only of elephants, or in another case only of chairs, then what would happen is largely the first layer would consist of the same kind of features that we've seen here. The higher layers up to the last would generate features that are much more semantic in nature. This is a slogan that's out there. It's what the people in this field believe. And I'm simply exposing you to this idea and taking you through some concoction of slogans that underlie this. The relation to the theories that we will discuss is that the theoreticians are very good at understanding why these things emerge, where they're coming from, how optimization leads to these things, and they're less able to explain what's happening up at the top. But because they've got a really good idea down here, they're hoping that they can extend their theoretical understanding up towards the top. So that's the sequence of challenges that would have to be faced, is to understand how theory can predict the learning of parts and so on and so forth. So I didn't last time make very clear what ImageNet was about. I just crossed over it quickly. At one moment, it consisted of 14 million labeled images into 20,000 plus classes. The labeling required more than a year of human effort, and in the spirit of modern times, it was significantly facilitated by Amazon Turk. I did mention the role that Fei-Fei Li and collaborators played in masterminding this and getting it all going. This is a rendition of some of the images there. They've been splayed out on a two-dimensional array using something that's intrinsic about the deep net representation that was learned in one particular case. So you can see that somehow it's possible to find some interesting retinotopy or some kind of spatial global organization of the image that's produced by the technology that we will be discussing. It's kind of interesting to blow this up and look at it carefully when you have a moment. Now, again, brute force works because there's a fundamental tool that's being used. And I spent some time talking about this last time. I'm just reminding you that the key thing is it's literally possible to use brute force and make assertions about something having solved a problem in the real world because the brute force is being used in a very disciplined way, where there's a training data set involving many images. There are competitors who have a common goal, hence the term common task, to learn a class predictor from the training set. And there's an objective, automatic scoring referee that can't be tampered with, and there can't be any self-deception in the process. So in these prediction challenges that are out there, such as the ILS VRC, which is the ImageNet competition, the close following of this paradigm is what makes it possible for brute force to actually yield results. For centuries before this, brute force would not have been believed. The thing that's really revolutionary here is that people actually believe that brute force can work because of the following of this paradigm. So I just want to highlight that. By following the paradigm across the years, we've seen, and I showed previously, that the error rate as measured in this case, well, this doesn't say whether it's top 1, but I think it's top 1 classification, has gone down and down and down clear through 2017. And so the following of this paradigm and the incredible excitement, which is why you're here, has led to many, many people working very hard at this. That combination of forces has led to this increase. Now, it's not necessary to believe that deep learning is the only way this could have been achieved. What I am showing you happens to have been achieved that way starting in 2012. The earlier iterations were not using these particular ideas. But it's been shown time and time again throughout the history of biometric identification that you have exactly this. And we can go through natural language processing, we can go through fingerprints, irises, facial recognition, things that have been around for decades and were solved before deep learning was known. It's always been this way. It's part of a paradigm. The paradigm works. So deep learning doesn't get the credit for that. What I'm more interested in is what deep learning does, and now that there are so many thousands of people using it, it becomes important to understand as a thing in itself. There's a question in back. Please, what's your question?
In principle, would the common task framework ask that you use the test set only once? So is there maybe a possibility that on something like ImageNet, we've actually started overfitting on the particular test set over the years?
Okay, I'll repeat the question. The question is that if you have a contest where there's a sequestered test set, but individuals are submitting many, many entries, is there some possibility that the test set no longer is purely test? The feedback effect that you get is creating some overfitting. Is that an accurate paraphrase for you? That's certainly a possibility. I'm not aware of major research on that. I think that the issue is probably it would be really important if you had frozen data and you could never get more. ImageNet started with only a fraction of the cases that it now has. So another thing that's been happening here, I believe, is that actually there were less data in the early days. It's also true that new data sets come along, and so there's a paper, for example, that uses 300 times as much data as ImageNet. And so it's possible to see quite clearly that if you start with the ImageNet solution on this vastly larger data set, you do pretty well. Of course, you can then train on the vastly larger data set and you'll do even better. But you're getting close to the advertised performance. Yeah, there'll be some over-optimism, no question. Other questions since we're at it? Please.
Do you think characterizing it as brute force is like brute force naively would have to explore exponentially number of possibilities in dimensional space, but seemingly deep learning is much more successful, much more efficient than that. So maybe it's not fair to characterize it as brute force.
Well, what I mean by brute force is compared to having a theory that tells you where to look. Like there isn't some theory that says this kind of network is going to do better than that network because we have a predictive understanding of what these things do. Within some little playground or sandbox with various knobs you can tweak, it's simply brute force. Now, those knobs and so on maybe required inspiration, and you know, I'm not going to begrudge Jeff Hinton all his prizes of $1 million and stuff like that. That's not what I mean. But the work of people doing things with deep nets right now is dominated by just running massive computational experiments, doing a lot of things blindly, having no idea whether they're going to work or not. Just trial and error. And that starts at the simple initialization of the fundamental algorithm. Nobody really has a clue exactly what makes it initialize right, and you just try a lot of them. That sounds like brute force to me. I agree it's brute force within limited scope. Okay, so these are some of the images, and so anyway, we understand that the way the game is played is based on this empirical data set. There are obviously many issues that could arise, such as the question that was previously asked. Statisticians, for centuries really, have always worried about whether a data set is a good representation of the world that's out there. You can always have problems in your data that arise and cause your learning to backfire. So we'll have more about that later in the term. Okay, what I want to do now is just take you through enough of the basic machinery so that the little emblems that I put up for this lecture will have a clear meaning to you, rather than just be some sort of, eye candy. I also want to mention that at our website we have a cheat sheet which enumerates order of magnitude 50 or 100 things that you have to know about this field. So there are terms that people just talk about: ResNet, VGGNet, CFAR database, et cetera, and we've got a long list of those with a couple sentence description of each. So if you just cram according to that cheat sheet, you can pick up a lot of the lingo and culture quickly. I'm not going to go into detail in lectures, but I think it will really save you quite some time to get oriented if you go to the cheat sheet at our website. Okay, so the basic element here is something that already in the 1950s people were thinking about, sometimes called perceptron, sometimes called neuron, synthetic neuron, mathematical neuron, whatever, artificial neuron. The basic idea is there's a sequence of real numbers coming in, and each one of these nodes here represents a single real number. There's a sequence of weights that are attached to these edges, and this convergence of the arrows at a node here means that we're summing up all of these input values times the weights and producing just that simple dot product. There's a term B called the bias. So what actually comes out of this is a scalar that's an affine function of all the input values. And then, and this is very important because later there'll be diagrams that omit this part of it, but it's crucial for everything. Then there's going to be a nonlinearity that will be passed through. And you will see different notations for the nonlinearity by different authors. In this diagram, it's F. In some other diagrams, it might be sigma, etc. There's several families of nonlinearities that are considered commonly. So these could include the Tanch nonlinearity, just an indicator of being positive, so it's a kind of heavy-side nonlinearity. There's as well the sigmoid, which is or logistic curve to statisticians, and then ReLU, or positive soft threshold, to statisticians. So those are some examples that people use. Traditionally, this was in use, and then over time, this has been something very popular in recent years. So that detailed diagram is often replaced by a simpler, more coarse diagram that would look like this. So here the green nodes represent the individual components of a vector x naught. So that's similar to before. There's arrows coming out. That's similar to before, but before we focused on one node here and just all the numbers coming into that one place. Now we have a vectorial output. There's no necessary relation between the number of inputs and the number of outputs. Now, instead of it being collected here as just a dot product and that's it, since we've got a vectorial output, it's easier to think of this as multiplying by a certain matrix, namely x1 is w1 times x naught. But in addition, there's a scalar nonlinearity that's being applied point by point, and that's implicit now. But what's going to come out of this, if there's any arrows coming out again, you're going to have put the value that arrived out of the inner product here will have been fed into a nonlinearity. Okay, and in complete generality, to go back to the details here, the weights that you see coming into one of these artificial neurons, the bias and the nonlinearity, in complete generality, they could be just changing willy-nilly. Namely, when we have a collection of these, you could have completely different things going on in each case, in principle. But it's often true that certain restrictions are put so that, for example, the weights have a consistent relationship from node to node, or that the nonlinearities are always the same at one layer, etc. The same biases might be used, etc. So there may be constraints, but in ultimate generality, there could be a huge number of variations going on even within one of these structures. Now we can create multiple layers, and I'll just remind you that in each case what's happening is there's a linear combination coming in, producing an affine result on the inputs, and then going through a nonlinearity, and then going out again to each of several layers, several neurons in the next layer. So this will be called the first layer, the second, so on and so forth, and then this would be called the last layer. So hiding under here are all sorts of parameters, the weights, the properties of the nonlinearity. We had the biases, but they've somehow disappeared, and one way that can be done is by fusing into the inputs a synthetic 1.0. So there's always an input of 1.0 feeding into every neuron, and then whatever the weight is on that guy is actually your bias. So there are various, conventions that people use. So this is the simplest thing. You've hidden the biases and you've hidden the nonlinearities. So the calculation flow that we've just discussed is sometimes called forward pass. And if we had capital L as the last layer and the input as layer 0, then we've got an input x0 producing an output xl by this very simple loop. In each case, there's a matrix multiplication, there's this nonlinearity, now called sigma, so don't get weirded out that the notation has changed. And there's an implicit bias as well. Okay, so this diagram and this little loop, they sort of are the same thing. This one is obviously much more explicit and actionable. The other one is a little creepy. Who can figure anything out from something so vague? But it's commonly used that way. Okay. Okay, now you've got this network and it's got all these parameters, the W's that have to be learned. So those are matrices layer by layer, there are biases, so on and so forth, and maybe in addition some other details. So one way to look at this is that you've got a series of training examples. So say n images, and we represent each image as a vector. So maybe just vec out this array into a long vector, and then associated with each image there's a label like, ooh, cat, dog, car, something like that. So we've got images, labels, and then if we run a network with a given architecture and given weights, well, then the forward pass is going to give us a perfectly defined set of outputs that we'll call XIL. And we can consider as an objective some particular cost function. In this case, we've chosen an L2 measure, so it's saying that across all of the images, I'm sorry, that should be N, across all the images we want to match the output with the actual labels. Okay, and of course that won't necessarily be perfect, and it certainly won't be perfect if we just do a random initialization of this algorithm. We'll just get something. Okay, but then we're going to say if anything we can get, we can improve. And, you know, we go back to some of the old standards that everybody knows. So a traditional idea is gradient descent on anything that we would like to do, and that would just involve taking the weights and biases and perturbing them by going downhill on the gradient. So in principle, this would have to be calculated. Well, in principle, this is something that we could calculate quite explicitly, provided we can differentiate the outputs xi in terms of the underlying parameters of the network. And so there's no question that we can go downhill. Obviously, gradient descent has many well-known problems, in particular in high-dimensional spaces. So I would never even imagine that this could have a reasonable chance of doing anything, but it seems to have done quite a lot. Another element, I mean, Newton was great, but Newton would never have tried this on this problem. He would just the steam would come out of his ears. Come on. A key thing that I want to mention is this is just motivational. It's not what people actually do. What they actually do is stochastic gradient descent. Namely, instead of literally finding the gradient, they come up with a statistically estimated gradient by looking at a randomly chosen subset of the data that they then compute an approximation to the gradient in the same way that the Monte Carlo method allows you to compute an approximation of a population quantity, like a sum across a whole population. We can do the same thing by Monte Carlo. And then there are various refinements. There's mini batches where we can, for computational or other reasons, take little groups of data that we fetch from storage and compute some of the terms that go into the gradient on those groups of data. Then we could possibly amalgamate those with sums from previous groups with a forgetting factor or by other means. There's a variety of tricks which I'm not going to delve into, but these are quite important in building actual systems. The good news for things like this is that they're just simply little knobs that you can turn associated with systems like PyTorch, TensorFlow, and so on that are just simply going to handle all those issues for you. Now, backpropagation or backprop is a term of art that is used heavily in this literature. And basically the idea is if we want to optimize a Lagrangian, say, that has the form of what we want to minimize, as well as a penalty term here that's associated with what we want to constrain, then backprop allows us to go downhill on this Lagrangian. The constraint here is just the forward pass. Namely, we're just constraining that the output be what's produced by the forward pass that we've already spoken about. And going downhill along this, provided we're actually literally obeying that constraint all the time, would literally be just going downhill on this objective. But as you can imagine, there's a possibility for some misfit in this at a stationary point that should be cured. Okay, you can derive the backpropagation algorithm in this sense. And by the way, I wasn't able to compile the last hour or something before this, so there's a lot of things that I wanted to get into the slides that have to be put in. Those include credit in a scholarly sense for various things. Jan LeCun has a paper that uses essentially this approach to derive this algorithm, and in the posted slides that will be made clear. So in backpropagation derivation, we look at the derivatives of the Lagrangian with respect to the various parameters. Now there's Lagrange multipliers in that Lagrangian, and then in addition there's the derivative of the Lagrangian with respect to the different components x that arise at all the intermediate layers. Then in addition, there's a backward pass, which implements a kind of formal adjoint relation that defines some auxiliary variable z's, and using those variable z's, the step of updating w using the derivative of the Lagrangian with respect to the components of w can be written very conveniently. So these are the weights. You recall these are matrices that are stacked all together. They're called weights, and then they're updated according to this simple rule. Yes, was there a question?
What's the function of L? What's that, the function of FL?
That's the sigma.
Oh,
Well, the reason is like, okay, so Jan LeCun uses this notation, so we want it to be like sort of use the same notation.
okay. There was something called little f on the first slide. Then there was something called sigma on the next slide. It's now f sub L. Sorry. We'll have to fix that in posting these as well.
It's just the activation function.
Yeah. I mean, the relevant activation functions. So you have different activation functions potentially at different layers and so on. Okay, so the structure that we're talking about can be traced way back. I would encourage you to look at a survey paper by Jürgen Schmidhuber about the history of the subject. Has a staggering number of references in it. And you can go to our Canvas website and see a copy of it, or you can obviously find it just by a simple Google search. One place where this architecture is quite explicit already is in a paper publishing the so-called neocognitron by Fukushima in 1979. During the 80s, it was worked on a little bit, but the computing power and so on was not there to get the spectacular kinds of results that we're aware of from the recent successes. However, Jan LeCun was able to do experiments combining convolutional neural networks with backpropagation, getting preliminary results already in 1989. Later, by the end of the 90s, there were results showing that you actually could use this architecture to get quite good results in handwritten character recognition. So in those days, it was a tremendous effort to do it. There are all sorts of details in this particular diagram about exactly how the problem was set up, and it's very specifically handled because of computational burden in actually carrying these things out, so that the image that you're trying to recognize has got to be registered and cropped in such a way that it all fits in a 32 by 32 patch. And then there are going to be a series of convolutions combined with some things that we haven't mentioned yet, like subsampling. These are all particular elements in the art that makes it, but it definitely has the general structure we've been talking about, but with many tricks that were found to be helpful in those days, and some of which are still in use as being fundamental. As I pointed out the other day, the excitement about these networks really began in 2012 when a team from University of Toronto were able to win the ImageNet challenge with quite a large margin, about 10 percentage points over the second place team. And they had a very particular architecture that they chose, and this is just extracted from their paper. Again, it has some of the ideas that we've talked about, but there are details in here where we haven't actually given enough terminology for me to explain what they are. You can still see that there are hierarchies, and you can see that there are completely connected things happening at the end. As it turns out, they don't use complete connectivity in the first few layers. They use only local connectivity with a certain neighborhood structure. And more than that, the connections are stereotypical, namely there's the weights have a spatial invariance. There's in addition a step here called max pooling, which we haven't discussed. So many things came together that were the result of experimental work, again according to the paradigm that we've discussed, and they produced a significant gain over other methods that were available at the time. An element that was present here was the use of ReLUs rather than the use of sigmoids. There was a concept of local response normalization, which seemed important at the time, but has since dropped away. There's max pooling, which we'll discuss, and dropout, which we'll discuss. The nonlinearities that we've been discussing originally were all chosen to be saturating, namely like the sigmoid, they would rise for a while and then plateau. And that was found to cause slow learning. And so there was, at least a slogan around of why you ought to be doing something that instead doesn't saturate. Namely, it's just going like the identity function for positive arguments, but is like the zero function for negative arguments. And so you can imagine that if you had an input that actually needed to get to a high value, you would need several layers of nonlinearities saturating to produce a high value. So you can imagine that this would be of some particular importance empirically. Max pooling was another ingredient of AlexNet, and the idea there was to choose the maximal entry in every, when you were in a max pooling layer, that was a layer that did not work the same way as the layers we've previously mentioned. So there would be an exceptional layer, max pooling, and in that layer, what happened is data came in 2x2 blocks, and the largest element in the 2x2 block was then copied over. As a result, there was a downsampling that is induced. Namely, if you started out with a 224 by 224 array input, the output of the pooling step would only be 112 by 112. Dropout was a regularization notion that involved essentially, as you do your stochastic gradient descent, in the computation where particular x's are coming in to some computation, you might just mutilate them at random and set them to 0. So a simple example could be that you set every other entry in the vector to 0. Even though you have perfectly good data, you're perturbing the data that you have in the training systematically. As it, this was not manifest as it was not an obvious thing to do at the time. It's understood from a theoretical ground now as being the same as what statisticians call ridge regression, but done in an online fashion. So what came out of the training in the first layer was features that look like long, thin ridges, and they're actually multi-scale. So there's some that are more localized than others. There's some that extend across the whole image. And you also get some interesting sinusoidal patterns. And then there's an ingredient here that I haven't mentioned, which is that if you're using color imagery, then we're not really working with real valued images. We're working with images that have vectorial values at each pixel. So it could be like RGB. You have some color representations, and then it's possible to understand the different basis functions that you're coming up with as possessing color attributes. Hence, you can have plots like this. Now, the different networks that have been constructed across these different contests have a variety of different attributes which we could discuss. Over here, one can list the classification accuracy, say, on the top 1 test, so that did you actually literally get the right label? There's also a top 5 test where you're just asking, did you get in the top 5 labels, etc. And over here, there's some measure of the size of the network in terms of how much computational effort is required to compute the forward pass. Then the size in this graph is indicating the total size of the coefficient set that's embedded in the weights and biases. So if you have more coefficients, there's going to be a bigger circle here. The circles are scaled in such a way that, for example, this is 155 million coefficients, and this is 5 million. So you're learning 155 million coefficients from 14 million images, each of some given size. So there's a significant amount of data, but there's also a very significant amount of coefficients, and they're roughly of comparable sizes. So you can see here that classification accuracy has gone up generally. Now the different networks here are known to people. If you read in the cheat sheet that we provide at the website, you can delve into, what is VGGNet, who made it, what are its attributes, what is ResNet, what is Inception, etc. So I'm not going to go into that. There's a variety of teams working on these things, and they've been successful in some iteration of these contests, and then someone comes along with a more successful iteration the next time, which has some new tweak or approach. So I might have said 14 million on the previous slide, but I guess the number of training examples is actually 1.2 million according to Vardhan's slide here. Whereas we're estimating more parameters than we have training examples, but each training example has a lot of data embedded in it because it's an image. Question is, why are we not getting into trouble? And one reason is that there are explicit and implicit regularizations being done. One thing that's done is so-called weight decay, and statisticians will recognize this as putting explicitly into the Lagrangian a term that involves the sum of squares of the weights. The ReLUs that are being used also are known to be giving implicit regularization when the feature maps are sparse. Dropout, as I mentioned, is a form of ridge regression, and then by choosing the architecture of the network itself, it's been found that certain architectures seem to be better regularized than others. As I mentioned before, there were experiments done from a completely different angle by Bruno Olshausen and David Field in the 90s, doing unsupervised learning. So it wasn't the problem we're talking about here at all. It was just to learn a good basis for sparsifying natural images. And they found empirically by a regularization procedure that optimized sparsity, basis functions that are quite similar in a way to what AlexNet and many of the other networks are finding. So there's some precedent for thinking that optimizations can lead to these particular kinds of representations. And there's some precedent for believing that what's found in the first layer is somewhat independent of the task, which has turned out to be important in transfer learning and in a lot of current work. So this is a mystery still because there's an explicitly given non-supervised problem, and it seems to be doing something quite similar. At the same time, when the Olshausen field work was done, it was recognized that much of what Olshausen and Field were finding by learning from data resembled what mathematicians would be able to do by trying to find optimal representations analytically using mathematical ideas, not about data, but about how to sparsify objects with edges, for example, or with point singularities. And so it seems that there's a very interesting connection between what the first layer of these modern neural nets are doing and some math, and at the same time some neuroscience. I mentioned this before, but I'm just trying to underscore this point because it's again part of the story here that we'd like to pull across as we go through later lectures. I'll now review in more detail some of the interesting competitors. VGG came, of course, after AlexNet and had a number of interesting elements. First of all, instead of going 8 layers deep, it went in one iteration 11, and then in a later iteration 19 layers deep. It dropped the idea of local response normalization that was present in AlexNet, and it added in filters of different types, creating an extra wrinkle that wasn't seen in the previous element, so that the number of types of filters that were being put in actually went up as you went to deeper layers. In addition, instead of using the 7x7 local filters that were being used by AlexNet, so there was a locality of connection that existed in this one went even more local, but it would allow 3 layers of 3x3, and then it just turns out that that has a 7x7 radius. So the footprint of what can affect 3 layers of 3x3 is 7x7. However, there is an intermediate nonlinearity that's implicit in the scheme that would not have, that can't be reduced away. So definitely you're getting sort of an extra deal by extra nonlinear possibilities, but you're also gaining regularization because the number of coefficients that are appearing in these 3x3 filters is just less at each layer. So if you're imposing that the same coefficients be used at all 3x3 neighborhoods so that there's a translation invariance, there's just less to learn at each layer. So the eye candy here illustrates that they started with a 224 by 224 by 3 array. That's an image with RGB. And then they went on through having a variety of types. So at the first layer, they had 224 by 224 by 64 because there's so many different types of filters. And then 112 by 112 by 128, etc. There's a downsampling that's being done similar to the way that it would be done with wavelets. But what wouldn't have happened with wavelets is that we're increasing the number of types of filters as we go along, out towards the last layer. There are still max pooling layers embedded here in red, and the locality is given up at some point, and then everything goes fully connected after some point. One thing you can learn by enabling to go deeper is that the problem doesn't always get better when you have more layers. Normally, the math would suggest to you that there's a nesting property, and you should see a monotonicity of the achieved performance. The nesting property is that you can always install no-op layers that just pass their results along without changing anything. And so a deeper network can always contain a shallower one in some, trivial sense. But actually, the deeper networks don't always do better, and that's an instant that's sort of, you've got more parameters to estimate, they're harder to train, you're overfitting, et cetera, et cetera. So the simple algorithm of stochastic gradient descent may not be able to actually deal with what happens with increasing depth. And so all of these tricks that are being used to come up with particular proposed architectures are in some way experientially derived to do better with the kind of back propagation stochastic gradient descent that we have. Now, ResNet came out the next year, and it had the benefit of being able to go deeper because it introduced an innovation, which is skip connections, that allowed essentially the default of any layer is to be a no-op. Whereas previously the default of any layer was to just set its output to 0. By recentering the default to be at the identity operation, then you came up with the ability to go deeper and learn deeper. So that was an important contribution apparently. It's all now, again, using the trick that came out of VGG of only using 3x3 convolutions, but having many more layers. In addition, it put in the notion of decimation as a valuable parameter, so that there's a parameter called stride, and you could take a 7x7 input and create merely a 3x3 output by, instead of sampling with these neighborhoods every possible integer shift, you subsample by only dealing with, say, every other or every third, in which case you would have a stride of 2 or 3. Batch normalization is another idea that's come along as being valuable, where you take as the input data the original values, and then you take a batch of those and renormalize everything in such a way that the mean across the adjusted batch is 0 and the variance across the adjusted batch is 1. So this kind of normalization in batches has turned out to accelerate training, so it's been learned that this is particularly useful in connection with stochastic gradient descent. It's also claimed that the kind of random initializations that may sometimes blow up or backfire kind of work better when you do this. Please.
When you train with batch normalization and then it's now prediction time, what goes through your network?
Well, that's a good point.
So what's the question?
What goes through your network when it's prediction time? Because instead of dealing with the raw data, you're dealing with standardized data. So I mean, I assume there's a dodge. I don't know what it is. I would have to look it up. But that's a good point. So before posting, we need to do something about that. Yeah. So that's John Ducci in the back, by the way. He's a ringer. He's totally done canonical work on improving stochastic gradient descent. So it's like having the world's expert asking just a very embarrassing question at the key moment.
Vardan has a comment. Vardan has a comment.
Oh yeah, please.
What you have is two steps. One step is statistics like mean and variance, and the data, and the other one is free to give the data.
Okay. So the answer I think is that at prediction time, every node has an associated mean over the training data of its inputs throughout training and an associated variance.
Yeah.
And you normalize by those.
Yeah. And after normalizing, you scale it by something that you have. Which sounds a bit weird because why would you normalize in the first place?
Well, scaling is usually not just scaling some data.
Yeah.
Okay, our co-instructor Vardhan Papayan says that he thinks the answer is that during training, the answer to John Ducci's question about what do you do at prediction time if you've distorted the data during training. He says during training you're separately recording the mean of each input and the standard deviation of each input, and then you're going to be able to know how to do a standardization of the data using that extra little piece of information that's stored somewhere separately. So I hope I got that right. Okay, so if we compare ResNet with the architectures that were in use earlier, the one interpretation is that what we're getting at each layer is just what we need to do to refine the previous representation. So some sort of representation is already available at the first layer, and then the next layer is providing a kind of residual representation, something that is a tweak to the previous one. But many things are unknown about that viewpoint and could maybe lead to some interesting math questions. So as you can see here, depth as a function of time. So we have these classifier performances, so that ResNet was definitely an improvement over GoogleNet, which was an improvement over VGG, which was an improvement over AlexNet, which is an improvement over what came before the deep enthusiasm. And then the depth of the networks is indicated here. So these are shallow, then we've gone to 8 layers, then 19, 22, and that's shot up to 152. So the ResNet made it possible to train much, much deeper, and so definitely got us into the arena where we can say we're going to truly deep learning. On the other hand, depth is not the only parameter that you have here. You also have width. As I've mentioned, you can have filters of various types, and so you can have sort of coexisting at each layer various filters that are being learned. As a result, you could have something that has a very high width of layers, and it's been pointed out that you can also improve performance that way. It's not well understood which way should be better. Is there some reason that one way should be better than the other? You have these degrees of freedom, but there's no predictive theory which is going to settle these things at this moment. There are many questions that Vardhan has put in here about what is happening. We've at the first layer, if we tried to post-process the first layer with, say, a simple linear discriminant analysis, we wouldn't be able to separate the image classes. And yet, by the time things emerge out at the last layer, we're actually able to do simple linear separation of all of these things. How is that possible? What's going on layer by layer that is producing this result at the top layer? Another thing that's been learned is that the filters that are being learned in these convnets at the first layer are somewhat problem independent, so that, for example, it's possible to take someone else's first layer filters and plug them in just off the shelf into your new problem, and they may have been trying to find pedestrians in the images, and you may be trying to, you know, do something with recognizing plumes of smoke being emitted from buildings, and yet it'll turn out that it's pretty good just to freeze at the layer that was provided by this completely unrelated learning task. Now, you may do better than that, but you could already get some benefit from it. That's interesting because, of course, what mathematicians have done for many years is try to invent interesting mathematical representations that are problem independent. And these go by names like sinusoids, wavelets, ridgelets, curvelets, Gabor functions. There's all of these different things. They're really problem independent. It seems that there's something problem independent about what's being learned here. Jeff Hinton, in a kind of mea culpa speech that he gave some time ago, but is easy to find on YouTube, discusses the fact that somehow we're treating as a supervised learning problem something that seems to be in some way getting the same result you ought to be able to get by an unsupervised problem. But we don't know what that unsupervised problem is. We don't really understand why this is emerging. There's now new networks like GANs. So they're adversarial. I don't have time to continue with that at the moment. I'll just add in one extra set of slides that are associated with understanding what's going on. Now, the filters in the first layer of one of these convnets are easy to visualize because you just take the weights, and then since they match up with certain pixels in the image, if you just plot what the weights are on each of the pixels in their neighborhood, you have a plot. You can see it. If you're trying to understand what's going on deep in the interior of this, what's been proposed and is typically used is to solve an optimization problem where you try to find some synthetic image, that's your variable of optimization, that is going to maximize the output of the ith neuron in the network. So maybe we constrain the synthetic image to have a sum of squares of 1 or something, and then we try to solve an optimization problem. This is picking out the ith element of the unified tower of all the different internal pieces of the neural network. So we say, oh, you know, at layer 3, position 18, we want to see what the output was. So we're just symbolizing here the selection of that particular element coming out of the feed forward. We're trying to find an image that under feed forward is going to drive that thing up as much as possible. That image then we plot. So if you then take some network like VGG and you plot what you get, you see Gabor-like patches in the first layer. So just to be clear, each one of these little squares here is an image, and so this is sort of a rendering of a little image patch. And it's the image that is the best matched to be received by that particular neuron. Okay, now there are neurons that compute different types of filters, and that's what these different squares are. So as you can see here, there's 25 types of filters, and then each filter has a spatial footprint. So you're seeing the spatial footprint of each of those types. Is that clear? Then as you go to the next layer, there's again the same thing going on with a certain number of types of filters. But it's harder to understand what the spatial footprint of those things is. They get increasingly complex and abstract. You do, if you look out at the last level, you do see things that look like entire animals, faces sort of in the middle. Like there's some eyes here that I can see, and maybe different animals are here. So it's learning a series of coefficients that are in some way analogous to the grandmother cells that we showed pictures of neuroscience having discovered in recent years. And this is actually finding such grandmother cells. Now, there are variations on VGGNet, and here's another one that has a somewhat different architecture. The VD is that this is coming out of a particular work, Vidaldi. So you can then extend this idea and take a class of images like all the frogs in your database. You can create a prototype frog, and you can ask, what is the feature in this deep net that responds most strongly to the prototype frog? And that's what you get. And there's a frog there, and there's another frog and another frog. And there's like a bunch of frogs embedded in that one. Whereas if I ask the same question for a prototype goose, then there is a feature. I mean, there's an actual feature that you can pull out of the 155 megabytes, plot it out, and that's what you'll see. So it actually is memorizing what certain specific entities look like. That's what's happening at the high enough level, a memorization operation. Yeah, okay, I'm out of time. This was the diagram that I put up as just an emblem of what we were trying to accomplish in this talk, just to let you understand what it means when I say that the standard way people talk about these networks is they go from pixels to edges to parts, so on and so forth, and then the invariance at the low level and the object-specific nature at the high level. I think I've told you enough about the architecture of these networks that you can recognize what these elements are and be a little more clear than at the time that we started. Thanks for your attention.